Now, before we move on to looking at the Legendre transform of functions of multiple variables, there's one other thing here that I missed out in the previous video, which we can actually add in graphically. So when we looked at the differentials, we said that our original function here, f, if we were to find df by dx, it's going to give us the value of our s. And we also seen that the dg by ds is going to give us the value of our x. Now, we stated these and we derived them mathematically, but we never actually showed this one here graphically. So I've actually added this in graphically. So let's quickly talk through it. We have our original function here in black. So this is our function f. And we Legendre transform this function in black and we get the function which is in blue. And we know that the x-coordinate of the blue function here is going to be the gradient of the black function. So for example, at this point here, you can see that the gradient of this function here is 4.2. So this point here is going to map along to 4.2 in this axis here, which would become our new s-axis. And the height is going to be the point at which this black line here, which is the gradient, which is the tangent, cuts the y-axis. So that's going to be this height here. So this height here will become this new height here. So that's just the Legendre transform, and we've seen that many times before. So we were able to say that when we looked at the infinitesimals, that the df by dx, that is the gradient of the function f, becomes the new s value. So we already know that from what we've seen in the Legendre transform. Now, we derived it in the previous video that also the dg by ds is equal to x, but I never actually showed you that graphically. So this is it graphically here. If we were to take the new function g, which is the blue function, and we were to draw in the tangent at this point here, then you can see that the gradient of this tangent line here is a value of 2.1. But that value 2.1 is nothing other than the x-coordinate of our original function. So that's the x-coordinate of our original function here, which is the 2.1. So again, we can move this about and you can check it for yourself, and you can try and you can find different values. So there's another value there. We can say that with the x-coordinate of the original function is 4.8. Sorry, is 2.4. So that's the point 2.4 there. Goes up to this point here. And that 2.4 is going to be the gradient of the tangent of the Legendre transform function also at that point there. So we can see here we're going to have our dg by ds is equal to x, as well as our df by dx is equal to s. So I suggest that you open up this file and you have a little play about with it, and you'll be able to see the mathematics which we created in the previous video, and you'll be able to compare it graphically here. Now, just one further thing to note before we go. The function that we've chosen, f of x, is equal to x squared. Now, for this particular function, the tangent line for our original function, the line in black here, and the tangent line for our Legendre transform function, that's the line in blue here, happen to meet together on this axis. Now, that's just something that happens for this one particular function. If we were to change this function, you'll see that that is not the case. So for example, if I make that x to the power of 4, okay, you'll see that these two lines, they don't actually meet on this y-axis. So that's just something that's peculiar to the particular function f of x is equal to x squared. So we'll go ahead now and we'll look at the Legendre transform of a function of two variables, and then we'll generalise that up to a function of n variables. And later on in the course, we'll see that those n variables in effect will become the n degrees of freedom of a typical mechanical system. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.